So I think it is time to start. Good afternoon, everybody. Welcome to this TMS seminar. The seminar of today will be held by Dr. Andrea Di Giuseppe. Andrea is a researcher here at the Department of Physical and Chemical Sciences of the University of L'Aquila. He obtained his master's degree in chemistry here at the University of L'Aquila. Later, he completed also his PhD in chemistry here in L'Aquila, supervised by Professor Marcello Crucianelli and Professor Francesco De Angelis. Then he joined the group of Professor Luis Oro at the University of Zaragoza and as postdoctoral fellow, leading a project centered on the catalytic hydrofunctionalization of unsaturated hydrocarbons by an organometallic catalyst. In 2019, he got a contract as a postdoctoral research associate in the research group of Professor Polly Arnold at the University of Edinburgh. And 1 year later, he moved to the University of California, Berkeley as an assistant project scientist, where he developed new fluorescent serum complexes with photocatalytic activity. At the end of 2020, he came back to the University of L'Aquila as a researcher in organic chemistry. Currently, he is working in the design and development of organometallic compounds of the transition metals as catalysts in reaction of high added value. Today, he will talk us about catalytic deuteration of bioactive molecules and will show us how organometallic chemistry play a fundamental role in this field. Please, Andrea, when you want, you can share your screen and you can start.
Okay, let me share my screen. Second. Okay, second doesn't work. One second, I have some problem. Okay. Oh. I don't know if you can see something. No?
We see you, but not your screen.
Okay. Sorry. Okay, I understand where is the problem. Okay, sorry. Okay, yeah, okay.
If you know what is the problem.
Yeah.
Okay.
No. Yes. Now I know.
Now it works.
Yeah, the problem is that for some reason, let me see why can't. Okay. No. Okay, sure. Now I know why. Let me just start 1 second there. I'm sorry.
Okay.
Okay, come in. maybe with this. Works well.
Okay.
Can you see something?
Now we see your presentation.
Oh, okay. Thank you.
The first slide.
Okay. I'm sorry. I'm a bit.
No
I'm not so good with this program. So yes, it's my first time in Zoom, so I don't know how it exactly works. Okay. So oh, yeah. Sorry. Yeah. Okay. Now, okay, we can start. Okay, with the presentation. Okay. What's that? Okay. Hi everyone, and sorry, okay, for these things, but I'm new for using Zoom. So thanks, Luisa, for the kind introduction, and thank you to the TMS committee for the invitation. Today, I would like to show you something maybe a bit different, a topic called for someone heavy drugs that is not cocaine or heroin, but bioactive molecules containing a heavy isotope like deuterium. I will show you their properties and how it's possible to introduce deuterium in a specific place of a molecule. Okay. Let's start refreshing some basic concepts about atoms. Atoms contain three basic particles: that protons, electrons, and neutrons. Okay, the nucleus of the atoms contain the protons positively charged and the neutrons without charge. Okay, the othermost region of the atom are called electron shells and contains the electrons that are negatively charged. So something important is this: more than 99.9% of atom mass is in the nucleus, and depend on the number of protons and neutrons that have approximately the same mass. Okay, atom of each element contain a characteristic number of protons. In fact, the number of protons determine what atom we are looking at. For example, all atoms with 6 protons, okay, are carbon. With 1 proton, hydrogen, 2 proton, helium, and so. Okay, the number of protons in an atom, okay, is called the atomic number. Okay, atomic number. Okay. In contrast, the number of neutrons, okay, for a given element can vary. Okay, can be different. Okay, so together, the number of protons and the number of neutrons determine an element mass number. Isotopes are 2 or more type of atoms, okay, that have the same atomic number, so the same number of protons, please student take note, and the different in mass number due to the different number of neutrons. Okay, while all isotopes of a given element have almost the same chemical properties, they have different atomic masses and physical properties. Okay, so remember, isotopes are basically the same chemical properties but different atomic masses. This is the most important. In this case here, you can see carbon 12, carbon 13, and carbon 14. 3 isotopes of the element carbon, okay, with the mass number 12, okay, 13, and 14, respectively. The atomic number of carbon is 6, which means that every carbon have 6 atoms. 6 protons. So the neutron number of this isotope are 6 for carbon 12, 7 for carbon 13, 8 for carbon 14. Okay, This number represents the abundance of a chemical element. This value measures how relatively common the element is. For example, in this case, carbon 12 is the 98.9% of the carbon in the Earth. Carbon 13, the 1.1%. Okay? Anuclide is a species of an atom with a specific number of protons and neutrons. For example, carbon 12 is a specific nuclide and contains 6 protons and 6 neutrons. Carbon 13 is another nuclide that contains 6 protons and 7 neutrons. Okay, so please, students, remember this term. Okay, the term that you have to use when you are talking about a specific type of atom like carbon 12 or carbon 13. Okay, so remember this term, nuclide. Hydrogen. Hydrogen has 3 naturally occurring isotopes denoted as hydrogen 1, hydrogen 2, and hydrogen 3. Hydrogen 1 and hydrogen 2 are stable, while hydrogen 3 is radioactive. Okay. Hydrogen is the only element whose isotope has different names that remain in common use today. The hydrogen 1 is called protium, hydrogen 2, deuterium, hydrogen 3, tritium. The symbols D and T are sometimes used for deuterium and tritium, and UNIVAQ accept the symbol but recommend the use of the official symbol, so hydrogen 2, hydrogen 3. Hydrogen 1, or protium, is the most common hydrogen isotope with an abundance of more than 99.985. Okay, so we can assume that the natural hydrogen in first approximation is composed exclusively by protium. Isotopes could be used for a wide range of applications. One of the most important applications is the labeling of organic molecules. Isotopic labeling is a technique used to track the passage of an isotope through a reaction, a metabolic pathway, or a cell. Okay, in this technique, the reactant is labeled by replacing specific atom, okay, by their isotope. The reactant is then allowed to undergo the reaction, and the position of the isotope in the product is measured to determine the sequence the isotope atom follows to in the reaction or in the cell metabolism. Okay. The nuclide used in isotopic labeling may be stable nuclide or radionuclide. In the latter case, the labeling is called radio labeling. Okay. The principal application of this technique is the investigation of reaction mechanisms in general. The study of metabolic pathway is another kind of reaction mechanism, and proteomics. Okay. But how can we detect the presence of an isotope in a molecule? Basically, there are 2+1 techniques depending on the type of isotope. Okay. First, if your substrates contain a radioactive isotope, okay, you can detect the presence of these substrates or metabolic of these substrates by radiation detectors. Okay, maybe not this, but things like this. Okay, more universal techniques to detect and measure the presence of isotope in molecule are the the nuclear magnetic resonance, or NMR, and the mass spectrometry. The NMR measure the interaction of a nucleus with an intrinsic nuclear magnetic moment with the magnetic field in our spectrometer. The problem of this technique is that only few nuclei are NMR active. Okay, so you have to show this nuclide for the labeling. Okay, so it's not too universal. The most universal technique is the mass spectrometry, because it's a technique that is used to measure the mass to charge ratio of ion. Basically, it's a technique that can weight, okay, the molecules. And as you know, molecules contain different isotopes, have a different weight, so you can detect these isotopes with this technique. Okay. In this slide, we can see an example of isotopic labeling applied to understand our reaction mechanism. This is an easy reaction. Is the esterification of a carboxylic acid, okay, with an alcohol. The elucidation of the mechanism of the reaction introduced the question of which starting material, carboxylic acid or alcohol, the oxygen atom of the ester come from. So the oxygen atom, this oxygen atom come from the carboxylic acid or the alcohol? The question can be answered by an isotopic labeling experiment in which the alcohol is labeled with, for example, in this case, oxygen 17, that is an NMR active isotope. So when the reaction is carried out with an oxygen 17 labeled alcohol, in the end of the reaction, the oxygen 17 isotope is exclusively found in the ester and not in water. Okay. This is indicative of the fact that a nucleophilic attack of the alcohol oxygen atom occur on the carboxylic acid, the carbonyl carbon. Okay. But today I would like to introduce you in the world of deuterium labeling. Why deuterium? Deuterium is one of the most versatile nuclide that you can use to label molecule. In fact, basically, CH bond is an ubiquitarian moiety. So you can basically deuterate every kind of organic molecule because they contain CH bond by replacing an H with a D. Okay. Also, deuterium is the cheapest nuclide because the source of this nuclide is heavy water. It is easy to obtain from natural water by the Girdel sulfide process. Okay. Protium is active in NMR. Okay, but deuterium is silent, so it's easy to detect its presence and with this technique and locate the exact position of the deuterium in a specific molecule. Here you can see the NMR of this molecule. Okay, at the bottom you can see the normal molecule. Okay, the protonated molecule with hydrogens, and at the top you can see here another molecule, same molecule, but labeled here and here. Okay, so here this molecule contains CH3, a methyl. Here contain a CD3. Okay. As you can see in the left of the spectra, this part, basically the two spectra are exactly superimposable. This is because this signal come from this CH, this 1, 2, 3, and 1, 2, 3 CH. Okay, that are the same for the two molecules. But in this region, okay, the normal molecule has a big signal, okay, have a big signal, but the deuterated, okay, compound is silent. This really small signal that maybe you can appreciate is because the molecule is only 99% deuterated. So the small signal is due to the presence of a residual procium atom here. Okay. And finally, one of the most important consequences to replace CH with a CD group is the possibility to measure a strong kinetic isotope effect, or KIE. To understand the KIE, firstly, we have to discuss about the concept of relative atomic mass. Okay, first, the atomic mass is the mass of an atom. Okay, the definition is a bit weird, but for us, this definition is enough. Okay, the mass of an atom. Here, you can see two isotopes of samarium, samarium 144 and samarium 154. Okay, as you can see, the difference in the weight of these two isotopes is a lot, it's 10. Okay, this is the same atom, okay, but 10 is a lot. But in the case of hydrogen, if you take the weight of hydrogen and deuterium, you can see that the difference is only 1 unit, okay? But samarium has a big atomic weight, so the relative increase in the atomic mass between the two isotopes is only the 6.5%. In the case of hydrogen, the increase in the mass is huge, is 100%. So basically you can imagine protium and deuterium like two twin, okay? One fit twin, it is the hydrogen, and a super fat twin, that is the deuterium. Okay, now the kinetic isotope effect. To explain properly the kinetic isotope effect, maybe we need a week. So I will try to introduce just something in 2 minutes. Okay, the red one is a Morse potential curve for the 0-point vibrational energy of two isotopic bonds. Okay, these two. The epsilon axis is the potential energy, and the x-axis is the internuclear distance. Okay, this figure, ED0 and EH0, correspond to the 0-point energy of CH and CD. The 0-point energy is the lowest possible energy of a system. Okay, the lowest possible energy of a system. 0-point energy depends upon the reduced mass of the molecule. So the heavier the molecule or atom, the lower the frequency of vibration. Okay, so heavier molecule and atom, so lower frequency vibration, and smaller the 0-point energy. Lighter molecule or atom have greater frequency, okay, of vibration, and higher 0-point energy. So deuterium is 100% heavier than hydrogen, and therefore has the lower 0-point energy. This results in different bond dissociation energy. Okay, different bond dissociation energy for CD and CH bond. In particular, the bond dissociation energy, this for CD is greater than the bond dissociation energy for CH. Okay, this difference in energy due to isotopic replacement results in a different rate of reaction. Okay. and this effect is called kinetic isotope effect. Okay. So the reaction rate for the conversion of CD is basically slower than the reaction rate for the conversion of CH. So you can remember basically this, that greater the mass of the isotope, more energy is needed to break the bond. Okay, greater the mass of the isotope, more energy is needed to break the bond. So basically, CD bond results kinetically more stable than a CH bond. Okay, in this slide, we can see a clear example of kinetic isotope effect. The reaction is the bromination of acetone. Okay, when an hydrogen, when hydrogen was replaced by deuterium, this reaction, KH under KD of 7 was found. So basically, it means that this compound, the deuterated acetone, react seven times lower than its protein counterpart. Okay, 7 times lower is a lot. It's a lot. And why we are observing this huge difference? Okay, this is because the rate determining step of this reaction, is the tautomization of acetone that involves the breaking of this bond, a CH bond. Since the breaking of a CH bond is involved, a substantial isotope effect is expected. Okay, now it's time to introduce the deuterated drugs. Okay, drugs are typically a xenobiotic compound. Okay, the body removes xenobiotics by xenobiotic metabolism. Okay, this consists of the deactivation and the extraction of xenobiotic, and happens mostly in liver by oxidation mediated for example, hepatic microsomal cytochromes. So in this reaction, a specific CH is transformed in a COH, and the molecule becomes more hydrophilic and easier to be eliminated. But for a drug, it has to trigger some kind of beneficial effect. These metabolism represent a drawback. One for the deactivation, and two, in some lucky cases, for the formation of toxic secondary metabolites. This problem can be partially solved by chemical modification, introducing a bi-isoster group. What is this? Bi-isoster are chemical substituents with similar physical or chemical properties, which produce broadly similar biological properties to the protein, to the another chemical compounds in general. In the case of CH, the most important bi-isoster is the CF. Fluorine substitution, although certainly a proven way to avert oxidation at a specific site of replacement, but is massively different in so many properties relative to the hydrogen it is replacing. Yet you can see some of these properties. The CH bond may be substantially more stable to oxidative processes, especially CH bond, because of the kinetic isotope effect. More specifically, the Deuterium kinetic isotope effect. So the CD switch will give results that are clinically identical to the protein version, whereas the CF analog will give different results. So the change to CF, okay, change potentially everything. The switch to CD change almost nothing except the chemical route to obtain this compound and the rate of oxidation. Okay, the rate of oxidation. So basically, the CD, the atomic pair, is the 1-2 non-radioactive bioisostatic, bioisotopic, isoelectronic replacement for the ubiquitous CH bond. The very first example of the deuterium recuperation bioactive compounds date back to the 1961, okay, when these two independent groups report a decreased metabolism for D2-tyramine and D3 morphine, okay, compared to the parent compound with hydrogens. But the breakdown in this field was April 2017, with FDA approved the first deuterated drugs. Name is so weird, is deutetrabenazine, okay, for the treatment of this disease. This new compound improved the pharmacological properties of the parent protein compound, presenting a reduced number of daily administration. But so one of you can think that this deutetrabenazine is just a curiosity, but no. The race to the heavy drugs has begun, and in fact, in this slide, you can find a little collection of deuterated compound entered in clinical development. A lot of these are in phase 3 for different diseases. Okay. Now I would like to show you 2 examples of deuterated drugs and why in some cases they are so effective. The first example is the D3-L-DOPA, that is the deuterated analog of levodopa, okay, used for the Parkinson's disease. So after the carbosylation, okay, mediated by this enzyme, the metabolism of this D3 dopamine, okay, can be tuned by deuteration. In fact, the incorporation of deuterium at the alpha carbon slow down MAO activity and slow down the formation, okay, of this metabolite. While at the beta carbon, okay, the other carbon, the duration of the other carbon, attenuate the DBH functionality with consequent reduction of this metabolite. Okay, so basically, the result is that D3 levodopa is more potent anti-akinetic compared to the traditional levodopa for Parkinson. Okay. Next example is the incorporation, okay, of deuterium in the alpha prime carbon in ifosfamide, okay, a chemotherapy medication used for the treatment of a number of types of cancers. So this is a weird effect, but it's really nice. The deuteration, okay, of this specific position results in an enhanced hydroxylation of this position, the 4' position, while reducing the N dechlorination compared to the no deuterated drugs. These, the metabolic shunting favoring the 4-hydroxylation, okay, over the N dechlorination is noteworthy, as the latter lead to more toxic and less efficient metabolites, such as this, the chlorothaldehyde, okay, responsible for the nephrotoxicity, nephro with P. Okay. Now, imagine that you have a drug and you have a problem with the oxidative metabolism, okay, of this drug. So, one idea to slow down the metabolism, this drug could be the deuteration of all the CH position, no? This is called per deuteration. Maybe it could be a nice approach, but have two big problems. The first problem is the per deuteration of a molecule in general is to be a really, really expensive procedure. Okay. The second problem is a bit more weird, but is that the deuteration of a position can have some detrimental effect in the deuteration of another position. For example, look this molecule. From the metabolism of this molecule, we can take this metabolite that is hepatotoxic. Okay. So the deuteration, okay, the deuteration of this method, okay, deuteration here, significantly reduced the formation of the metabolite. Okay. But no improvement or slightly detrimental effect were instead observed when further deuteration, okay, so this and this were performed. So this suggests that more is not always better. Okay, so if you know the size of metabolism of your molecule, okay, the best approach is a selective deuteration of each one of your soft bond. Okay. Okay, but how can we level a molecule in a specific position? There are two possible approaches. Okay, the first one is the classical one, the classic multi-step synthesis. This is a really powerful approach. Okay, but that's a lot of problem. First of all, low atom economy, and there is a lot of wastes. Okay, second approach is the selective, okay, the selective HD exchange reaction mediated by catalyst. Okay, by a catalyst. This approach is very more efficient and have reduced the amount of wastes. And often, when you work in this condition, you have mild conditions with respect to this classical multi-step synthesis. Basically, this is my work. Okay, I work in this field, so in the design and development of organometallic catalysts able to mediate different reactions. So I work in the optimization of the catalytic condition of the reaction, and finally on the determination of catalytic mechanism. And recently I started collaborating with Dompe for the development of a catalytic system able to mediate the selective introduction of deuterium in a biomolecule. In this slide, I would like to show you how work and how to design catalysts for HD exchange. Well, first, you have to know your substrates, especially the type of functional group and bond contained in its structure. Okay, but most important, you have to have a target, a CH bond target. Okay. Now you have to choose a correct combination of method and ligand in case of organometallic complexes, of course, that allow first the interaction of catalysts and substrates, and then the activation, okay, of the CH bond. Okay, but the activation only of the CH bond the target CH bond. So then your catalyst should be able to interact with some basically with the deuterated source. In some cases, it should be able to activate the deuterium source, okay, performing the HT exchange. And in the last step, the active form of the catalyst should be regenerated, okay, providing the substrate deuterated in a specific position. Okay. I prepared 3 examples of catalytic system, but time is over. Maybe I will show you just the first one. Just the first one.
Yes,
okay?
Thank you.
Okay. Okay. The first example is basically my first work in HD exchange 10 years ago. I was working with olefin, and one of the challenge, okay, was to obtain a catalyst able to mediate the selective beta-beta deuterated compound. Okay, as you can see here, styrene is a cheap starting material, but the beta-beta deuterated compound is really expensive. Okay, why? That's because the synthesis is a real bad synthesis. The yield is just 25%. It's a very dirty chemistry that use a lot of dangerous reagents. Okay. Okay. The only catalyst able to mediate a similar reaction was this rhodium-3 hydride developed by Milstein. The catalyst operates by this insertion beta elimination mechanism. Okay. In this mechanism, the hydride, okay, is deuterated by a fast exchange with the acidic deuterated solvents, like, for example, air water. Okay, so it's first deuterated, then an olefin insert in the rhodium deuteride bond. Okay, and now in order to have an effective deuteration of this olefin, this Phi bond have to rotate, okay, bringing the hydrogen, okay, close to the methyl, and in this way the hydrogen can be removed by beta elimination, regenerating the initial active species and providing the deuterated olefin. Okay, I know that it's not easy, but just remember this: insertion, rotation, beta elimination. Okay, just these three steps. So for this work, we prepared this rhodium-3 hydride complex, filling this ligand. This is called an heterocyclic carbene ligand. Okay, this is a bulky ligand that you can imagine like an umbrella. Okay, we tested this lovely complex as catalyst for the HD exchange of styrene with the D1 methanol. And we found that it was more active than the Milstein catalyst, and especially high selective for the deuteration of the terminal vinylic CH bond. Replacing this NHC with a bulky phosphine with a totally different geometry, okay, it's like this, the phosphine, both the activity and selectivity fall down, and the absence of a bulky ligand lead to pair deuteration of the olefin portion without any selectivity. So this evidence point out to the fundamental role of the carbene in the catalytic cycle. We explored other combination, and we found that changing basically a bit the NHC, we obtained a catalyst able to catalyze the S2C formation of beta-beta deuterosterine. If you see here, the deuteration in this part is 0. But how can we explain the role of the carbene? Okay, to explain the role of the carbene in this catalysis, we perform different experiment, okay, and DFT calculation.
Excuse me, Andrea, we don't have time because.
Okay. Sorry. Just
look.
yeah. The last yeah, the last slide. Basically, the rotation. Remember the mechanism: insertion, rotation, beta elimination. So the rotation was the step that make the selectivity. Why? Basically, because the carbene, okay, deny the possibility to rotate of one of the two isomers. Okay, so from these isomers you can obtain the deuteration in beta. From this isomer you can obtain the deuteration in alpha. But this isomer can rotate for the presence of the carbene. So the selectivity is explained for this particular words. Okay, this was the last slide. Thank you so much for your attention, and yes, sorry if I had the problem at the start of my intervention. Okay,
it happens. So thank you for your clear presentation. That's why. Okay. So thank you for a clear and interesting presentation on this very fascinating topic. If there is there are some questions from the audience, please don't be shy. Giovanni, please.
Hi. Yes.
Hi.
Well, I don't know anything about this topic, but I'm very fascinated by the organic chemistry that can be built with deuterium. You know, the first time I see something like that. So
yeah, it's really nice.
I'm kind of thinking very naively. It could be possible to have like a life form on deuterium in all of organic matter.
Yeah, no, in this form, because, for example, you can drink heavy water. Okay, it's toxic. Why? For this reason, for the kinetic isotope effect. Okay, because our system, okay, our biological system is made to use hydrogen, not deuterium. Deuterium is the fat brother. So the reaction with deuterium are slower. The reaction with the hydrogen. So a life with deuterium, of course, is possible, but with a system, okay, built for deuterium, not with a system built for hydrogen. Okay.
Maybe in another planet with a different.
Yeah. Sure.
Thank you.
Are there any other questions from the audience? Don't be shy. If not, I have a curiosity, a general curiosity. When you showed us your result, you showed also a part related to the computational result of a computational study based on the experimental results. I mean, which is the, I imagine that these two aspects of your research are strictly related. I mean, to rationalize the data that you obtain, the computational part is fundamental, or you can, because this is a very interesting aspect.
Yeah, Luisa. Yeah, it's I think, please. Yeah. Basically, yeah. If you will work in this world, okay, basically to prepare a good catalyst, to design a good catalyst, you have to know how it works, exactly how it works, and how the different part of your catalyst work together to get the final result. Okay, so to know these things, of course you have a lot of experimental data that you can take and you can manage, okay, these things, okay, but the theoretical chemistry, so the computational chemistry, help you a lot to understand how effectively a reaction can take place. For example, both.
Both are fundamental. Both are fundamental.
Yeah. That's the complementary. Yeah,
complementary. Yes,
yeah.
I was wondering this. There is a question from the Professor Teddy from the chat. Can you expand on the role of deuterium in the Big Bang nucleosynthesis? I'm not expert, just curious.
I'm sorry, but I don't know nothing about the Big Bang nucleosynthesis. I'm sorry.
Okay, you're not expert too, so
no.
we have to look for an expert. It was just a curiosity from.
Okay.
There are any other questions from the audience? Curiosity or something that you want to ask? So, if not, we thank Dr. Giuseppe for his presentation. Very clear, very interesting, and we will meet in the next Thursday for the next TMS seminar that will be held by Professor Francesco Masedu, who works here at L'Aquila at the Department of Applied Clinical and Biological Sciences, and the seminar will be entitled Building Up Evidence, Meta-Analysis and Systematic Reviews. So thank you and good afternoon.
Bye.
Bye-bye.